Hi everyone, welcome to another LIC class. In the previous class, we started op-amp multi-vibrator. One of the applications of op-amps is to use it as a multi-vibrator. What was a multi-vibrator? A multi-vibrator is a device that oscillates or switches between two stable states, a positive voltage and a negative voltage. The op-amp multi-vibrator are used in a variety of applications for creating digital clock, PWM signals, and I explained a little bit about PWM or pulse width modulation. For switching, using as an oscillator, again for clock, so on. There are a lot of applications from the op-amp multi-vibrator. We spend time on different type of explaining about how the op-amp multi-vibrator works and what is the principle behind it. At the heart of an op-amp multi-vibrator, we have an op-amp acts like a competitor, which has a very high gain, and the output actually switches between its positive and negative saturation voltage, or the positive and negative supply rail voltage. We also solved a practice problem to determine that saturation voltage. Today, we're going to speak about sinusoidal to rectangular conversion. So one of the many uses of this Schmidt trigger comparator, other than use it as an op-amp multi-vibrator, is that we can convert any type of signal, not just sinusoidal. We can use it to convert triangle, sinusoidal, and any type of signal that doesn't look like a rectangular signal to a rectangular signal. So we can use that as a converter as well to create perfect rectangular waveform. And in fact, this Schmidt comparator always produces a rectangular output waveform independent of the input signal waveform or the shape of the input signal. So if we give it, again, a sinusoidal, it gives us rectangular, a triangle, any type of signal that we give it an input, it gives us always a perfect rectangular shaped output. So the way this works is that, for example, if I give a sinusoidal signal to the inverting input of this op-amp, and we set this volt, imagine this beta, let's say that this beta is 0.1 volts. Make it 0.1 volts or 100 millivolts. 100 millivolts. We know that for an ideal op-amp, V reference, or which is V positive, would be equal to V negative. And if Vn, which is V negative, if Vn, which is again V negative, if this is greater than V positive, then the output voltage, V output, would be equal to negative VCC. And if Vn is less than V positive, then V out would be equal to positive VCC. So now here what happens, and you can see it from this graph as well. When V reference or Vn, and by the way, this sinusoid signal, this is our Vn. And this rectangular, this is our V out. Let's see, V out and Vn. Then when V reference is greater than V, Vn is greater than V reference, then V out will go from positive saturation to negative saturation. You can see here that the output voltage would go from positive to negative. And the opposite as well. When negative V reference is less than Vn, or in other words, Vn is less than V positive or V reference, then the output would become positive, V saturation. And the reason this happens again, we know that in an op amp, V out is equal to AV, V positive minus V negative. And for an ideal op amp, AV is infinite. In reality, the output, the maximum output that we can get from op amp is equal to its positive and negative supply rate voltage. Therefore, if V positive is greater than V negative, you're going to have the positive VCC, and if it's less, you're going to have negative VCC. So why here do we have V saturation positive and V saturation negative and not positive VCC and negative VEE? The reason is that in reality, V saturation is usually 1 or 2 volts less than VCC. So positive VCC, V saturation is usually positive VCC minus 2 volts or 1 volt. And negative V saturation is usually the negative VEE minus 2 volts. So if VCC and VE are 15, positive 15 and negative 15, usually VSAT is between positive 13 and negative 13. So usually 1 or 2 volts below that. The reason that we have 1 or 2 volts below that is because the op amp itself has internal resistance, which has a little bit of drop in the voltage. You're not going to have that supply rail voltage directly converted to the output. So now how can we change the frequency of this multi-vibrator? Simply we have 2 ways actually to do that. One, we can change the frequency of the sinusoid input, which usually is not the case. It's very difficult to change this frequency unless it's connected to a function generator. The other way to do that, which is the easier way, is by simply changing the reference voltage. So changing this reference voltage, instead of having the reference voltage here, if I have it here, then you can see that I can change the shape of the output signal. Or example, having this here. Yeah, let's make this one here. So if I have this one over here, it's going to be positive up to here. And if I have this one over here, so I'm going to make a narrower signal actually. So by changing this V reference, I can change the output frequency of the oscillating frequency of the system. So as the input waveform will be in a periodic and have an amplitude sufficiently greater than its reference voltage, V reference, the output rectangular waveform will always have the same period T and therefore frequency F as the input waveform. By replacing either resistors R1 and R2 with the potentiometer, we can adjust the feedback fraction beta and therefore the reference voltage value at the non-inverting input to cause the op amp to change state anywhere from 0 to 90 degrees of each half cycle, so long as the reference voltage V reference remains below the maximum amplitude of the input signal. So again, if V reference is greater than this, like here, obviously you can't switch anymore. So V reference should be between the maximum and the minimum of Vn. This is going to be V reference. So most of the time we don't have access to an input sinusoid voltage like we have here, the Vn. Another way to create a pulsating DC or a rectangular signal without having this Vn is that we can simply replace this Vn with an RC circuit. So if instead of this voltage, if I have something like that looks like if I have a capacitor here And if I add another resistor here, I create an RC circuit. And this RC creates a pulsating signal, which looks like this. When you give a capacitor a positive voltage, imagine I'm giving it, I'm going to draw Vn with the blue one. So if I give Vn to the capacitor voltage would slowly start charging until it's fully charged. So the capacitor voltage will look like this. And this is going to be my capacitor voltage Vc. It's not going to immediately follow and it's going to reach almost to the it's going to almost reach the voltage of the input. Just give me 1 second. And this voltage is our Vc. And if I change the input voltage or the voltage of the capacitor, for example, to a negative voltage, what happens to the voltage? So initially, imagine that the capacitor is fully discharged. We have a discharged empty capacitor and we connect it directly to a battery. The voltage of the capacitor is going to slowly increase until it matches the voltage of the battery. Then imagine that when it reaches its maximum, I reverse the polarity of the battery. Now, instead of going, for example, to positive 12, I switch the positive negative end of the battery connection to the capacitor. Then the capacitor starts slowly discharging and charging towards the negative. And if I have this cycle, I'm going to have a capacitor that looks like this. The voltage of the capacitor actually looks like this. It goes from positive to negative to positive to negative. Now I have a pulsating signal. It looks like a triangle signal. We actually call this alligator tooth signal. But it's not actually a sinusoid signal. So how can I use this in this op-amp? The way that we can use it in this op-amp is that actually we can create a multi-vibrator if I add this RC to the input of the op-amp. And how does this work? The way that this works is, it's actually explained here as well. So instead of having the input, we can put an RC, and using the charging and discharging of that RC, we can create a rectangular signal. The way that it works is like this, actually. Initially, imagine that the capacitor is discharged. So the capacitor voltage initially is 0. Okay. And imagine initially that the output is positive VCC. The output is positive VCC. Now we're going to have this positive VCC minus IR on this capacitor. So we're going to have positive VCC minus this IR on this capacitor. What happens to the capacitor when I put a positive VCC voltage on its terminals on this connected to a positive VCC? It's going to slowly charge. Am I correct? Yes. And imagine that this is VCC minus IR. This is the VCC. And IR is actually negative. So it's slowly increasing until it reaches VCC. But at some point, VCC would be greater minus IR, which is this small voltage here, would become greater than V reference. So it's slowly increasing until this VC, which is VCC minus IR, this is greater than V reference. What happens when Vn is greater than V reference? What happens when Vc or Vn is greater than V reference? Then the output would immediately switch to negative V saturation. Yes. So now the capacitor is trying to catch VCC, but suddenly now the VCC has reached negative V saturation. So this is saturation voltage, negative V saturation. See if I can, yeah. Which is VCC minus IR. The capacitor is trying to follow the positive voltage. It's becoming fully charged. It may be full charge, but it may not even. And now suddenly what happens is the output voltage is reversed, suddenly going from positive to negative. Now the capacitor, the polarity of the voltage is completely reversed. The capacitor is going to be discharged and the voltage is going to get negative. So now the capacitor would be discharged and the voltage is going to be negative. Again, at this point, VC would be less than V reference. And when VC is less than V reference, then the output V out would be equal to positive V saturation. So again, when it reaches this point, the output again would jump back to V positive. And you're going to continue this cycle. So the capacitor voltage looks like this, and the output voltage would look like a rectangular. So in the input, VC would look like this, and the output would look like a saturation. Actually, I'm going to draw it on this one so you can see. The voltage of the capacitor goes like this. And the voltage of the saturation would look like a rectangle. So we eliminated the need of putting a different signal generator in the input simply by adding an RC circuit. We can create a rectangular signal in the output. An RC circuit, the time for a capacitor to fully charge is equal to 5 tau, by the way. I think you know this already from circuit 2. And tau is equal to RC, which we call it the time constant of the capacitor. So it takes 5 time constant for the capacitor to go from 0 volt to its maximum voltage. And this is 5 tau. And tau is equal to RC. 5 tau. So usually we want this 5 tau RC to be a large number to be able to switch between these. And these are the explanations for the, do you want to take a picture of it? These are the explanations and the voltage of the capacitor here. You can read faster than I can. So first we will assume the capacitor is fully discharged. And the output voltage is equal to the positive saturation voltage. Then the capacitor will start charging until the voltage of the capacitor becomes greater than the reference voltage. At that point, the output voltage would switch to negative V saturation, and suddenly the output voltage that the capacitor sees is negative V saturation. Therefore, at this point, I'm going to put it point A, and at this point, the capacitor has to discharge and reach the negative voltage, and again at point B, V saturation again is going to be VC is going to be less than V reference, and therefore V out would be positive V saturation. And again, the capacitor should follow that positive voltage until it's fully charged. So the input will look like this, and the output will look like this. Now, what can I do if I want to change the signal frequency, for example? There are two ways. First, we can change the RC, but that's not recommended. Usually changing the RC, or if you want to add a variable RC, variable C in the circuit, those are very expensive, not very accurate, and are not recommended. But another way that we can adjust this frequency and adjust the width of the signal, or what we call the duty ratio, is by changing the beta point, or the beta voltage. So by adjusting this beta voltage, or the reference voltage, V beta, which is V reference, we can, to some extent, control this frequency, the rectangular frequency. And this is the continuation of the explanation. Once the op-amp's inverting terminal reaches the new negative reference voltage, negative V reference at non-inverting terminal, the op-amp once again changes state, and the output is driven to be opposing supply rail voltage. Therefore, it goes from positive to negative, and then negative to positive. I think these slides explain the situation pretty well. So how do we determine the reference voltage? Again, it's the same thing as the Schmidt trigger. The beta voltage is calculated using voltage divider, which is equal to R2 over R1 plus R2. And the period T is calculated using the following equation. It's going to be 2RC ln of 1 plus beta over 1 minus beta. And obviously frequency, we know that it's 1 over T, or period. R as the resistance, C as the capacitance that we see here. It's going to be this R and this C. We're not using R1 and R2 for this. And for beta, we're using actually that R1 and R2. But this RC is actually the RC circuit that is connected to the input of the capacitor. So the frequency of the oscillation not only depends on the RC circuit, but it also depends on the beta, or the reference voltage as well. Therefore, by changing this beta, we can change the frequency to some extent. But however, if we use resistor values that gave a feedback fraction of 0.462, then the frequency of oscillation of the circuit would be equal to just 1 over 2 RC, as shown, because the linear log term becomes equal to 1. So you're going to have a rectangular symmetrical output in the system. Now let's solve an example. Example number 1. Op-amp multivibrator is constructed using the following components. R1 is 35K, R2 is 30K, and R is 50K. And C is 0.01 nanofarad, or in other words, 10 pico. 0.01 microfarad, or 10 nanofarad. We want to calculate the circuit frequency of oscillation. Only equations that you need, we need beta, which is R2 over R1 plus R2, and the period T, which is 2RC ln of 1 plus beta over 1 minus beta. I'll give you 5 minutes to think on this. And again, the first student that solves this, I'm going to give extra points on their next assignment. Anyone solve the problem? What is the answer that you got? No one?
There's nobody calling right now. Let me know if you want to make.
Okay, let's see. Sorry, I don't know for what reason. What? 3.2.4. No. So beta would be 30 plus 30 over 35 plus 30, which gives us 0.462. T would be 2RC ln of 1 plus beta over 1 minus beta. So T would be equal to 0.001 second or 1 millisecond. And F would be 1 over T, which gives us 1 kilohertz. So then the frequency of oscillation is calculated as 1 kilohertz when beta is 0.462. And therefore, F would be equal to 1 kilohertz. We can take it one step further by replacing one of the feedback resistors with the potentiometer. Before that, I have another question. I think it will be helpful to just compare these two. Imagine that we have the same capacitor and the same resistor. Now let's make this 50K as well. Imagine that we have the same capacitor, but this time we have changed the resistors. I want you to again find the F. This is again a small quiz. Beta would be R2 over R1 plus R2. This one, R1 is 2K, R2 is 10K, and R is 5K, and C is again 0.01 microfarad. We want to find the frequency F. Does anyone have the answer?
10.
10 kilohertz. Okay. So I'm gonna actually leave this for you to solve at home because I don't have enough time, but beta again is gonna be 10K over 2 plus 10K. And then T would be equal to times 5K times 0.01 times 10 to the power of -6. The ln of 1 plus beta over 1 minus beta. And then finally, F would be equal to 1 over T. You can solve this at home. A simple math problem. So there's also another way to change the frequency. And you would, when we solve this, we realize that the frequency is a little bit higher around the 10K that you mentioned. So by simply changing R1 and R2 or R, we can change the frequency. The easier way to do that is to replace R1 and R2 or beta with a potentiometer. And changing that, adding a potentiometer between the R1 and R3, here, the second potentiometer between that, we can change the beta. And by changing the beta, we can change the overall frequency, the oscillating frequency of the system. So by adjusting the central potentiometer between beta 1 and beta 2, the output frequency will change by the following amounts. So if the potentiometer of the pot wiper is at beta 1, then beta 1 is R2 plus R3, again here. If it's at here, then we have these two combined. So beta 1 would be R2 plus R3 over R1 plus R2 plus R3. And if it's at this point, then beta 2 would be R3 over R1 plus R2 plus R3. So this is for beta 2 and that's for beta 1. Because at beta 1, we only have this resistor. Beta 2, we have only this resistor left. So for beta 1, we have R2 plus R3 over R1 plus R2 plus R3. For this particular example, if R1 is 100K, R2 is 100K, R3 is a 10K, then beta would be 0.524, and the frequency gives us F of 100 hertz. T would be 0.01 second, and F would be 100 hertz. Now, if we move the wiper, the potentiometer to beta 2 at this point, then we would have R3 over R1 plus R2 plus R3, which gives us 0.0476, and T2 would be equal to 0.82 seconds. Therefore, the frequency would go to 1.2 kilohertz. So the frequency range for this op-amp multivibrator is between 100 hertz to 1.2 kilohertz, anything between that. It couldn't go lower than 100 hertz. It could not go higher than 1.2 kilohertz. For this particular case, because we went to both extremes, beta 1 and beta 2. Now, a quick example. What if R1 is 10K, R2 is 5K, and R3 is 5K? We want to find beta 1 and we want to find beta 2. And I think we don't have enough time to find it for F1 and F2, but just beta 1 and beta 2. What is beta 1?
1/2.
Yes, 5K plus 5K over 10K plus 5 plus 5K. It's gonna be 1/2. And beta 2 would be equal to 5 over again 5 plus 10 plus 5 gives us 1/4. So beta 1 would be 1/2 and beta 2 would be 1/4. And we can calculate F1 and F2 based on beta 1 and beta 2 as well. In this simple example, we can produce an operational amplifier, multivibrator circuit that can produce a variable output rectangular waveform from 100 Hertz to 1.2 kilohertz. For any frequency range, we require just by changing the RC component values. We have seen above that an op-amp multivibrator circuit can be constructed using a standard operational amplifier, such as a 741 and a few additional components. These voltage-controlled non-sinusoidal relaxation oscillators are generally limited to a few hundred kilohertz because the op-amp doesn't generally limit. The op-amps does not have the required bandwidth, but nevertheless, they still make excellent oscillators. Again, these op-amps for a 741, the bandwidth is limited to 1 megahertz usually maximum. In reality, it's like 200-300 kilohertz. Therefore, these oscillators cannot oscillate above that because of the limitations of the op-amp. But if we use faster oscillators like the 441 series, we can generate megahertz oscillators as well. I think it's enough up to this point. I don't think we have enough time to explain the op-amp competitor. A few announcements next week. On Tuesday, we're gonna have a review session. On Thursday, we're gonna have our second exam. I have posted the additional material that you need for your final project. Please watch the videos, and I will spend the day after the second midterm explaining about the project as well. But I would highly recommend start watching the videos as soon as possible and learn how EZ88 works. If you have any questions about the upcoming exam, just please let me know, and I will see you on Tuesday. Have a great weekend.